Hello everyone, this is Kiran Kumar, and today I am going to continue with the problems related to trusses once again. For a better practice, I will go with the more number of elements in this case. This is the problem statement. Okay, so consider the 4-bar truss as shown in the figure. It is given that Young's modulus is equal to 2 into 10 raised to 5 Newton per mm square and cross-sectional area 100 mm square for all elements. Okay, so which are all the quantities that I have to determine? Let's look into that. So the first one is the element stiffness matrix of each element. So stiffness matrix I need to find out for each element, as well as stresses in the element and reaction forces. Okay, so these are all the parameters I should find out. Let us look into the actual the truss connectivity. Okay, this is the physical model. Okay, so where if you closely observe, he already partially given the FEM model itself. Okay, so in exam these things may be there or may not be there. Okay, but you have, let's take it as a simple physical model itself. So we are having 4 truss elements, 4 elements. So like this. Wow, this is the first one, second one, third one, and fourth one. So in this, one of the node is roller support, which is fixed by rolling support, and another 2 ends are having the what we call the fixed support. Okay, and if you go through the loading parameters, we are having 2 loads. One is 25,000 Newton, which is acting downward at this location, and 20,000 Newton, which is located at node 2. Okay, so these are all the parameters you first initially observe that. Okay, and dimensions is also given that it is of 40 mm and 30 mm. Okay, so these are all 2 dimensions that we observed. The next part is let's go to the steps involved in FEM. That is, first part is discretization. Okay, discretization of the domain. Okay, like as you observe, since we are having 4 trusses, let us go for 4 truss elements itself. Okay, so redraw the same structure, and later on redraw the same structure, and later on. So what you should do is you have to name the elements. Okay, let us call this as element 1, let us call this as element 2, and this as element 3 and element 4. After that, do the node numbers. Okay, node numbers in any manner you can do. Okay, so like now I am start with this position as node 1, node 2, node 3 and node 4. Okay, once you did all these, the next part is defining the axis. Okay, now to define the axis, let us have this as origin itself, and I am going to draw this location as positive x, and here as positive y. Okay, so this is much needed for defining the nodal coordinates and all. So likewise, this from here the origin starts, and it will take this direction as x and upward direction as y. Okay, so likewise you have to do that. After that, since we are familiar with the next part, so I need to create this table. Okay, so in which where I am going to define the nodal numbers and nodal coordinates, means the position of x and y. Okay, since we are having, you should look into how many number of nodes we are having right now. Here we are having node 1, 2, 3, 4, 4 nodes. So write down that, and positions. Okay, the positions of node 1 is, since it is at the origin, the x value is 0 and y value is also 0. Okay, next if I come to the node 2, since it is in the what we call horizontal direction, the node 2, that is x value is 40 mm and y value is 0. And coming to the node 3, so it's having x value of 40 and y value of 30 mm. And later the node 4, x value is 0 because it is in the y axis, and y value is 30 mm. Okay, so this is the way that you need to write down the nodal coordinates. And in addition to that, before going to the next element, I forget the complete procedure of this one. So where after defining the node numbers and element numbers, so at node 1 you have to mention the degrees of freedom as well as the forces. Okay, so like this, as you see, we are having 2 degrees of freedom at each node for trusses. Okay, node 1 is having q1 and the q2, q1 and q2, and similarly the external forces, let us call that as say f1 and f2. Okay, after that, coming to the node 2, it is starting from node 2, it is having 2 degrees of freedom once again, that is q3 and q4, and external forces f3 and f4. Okay, so after that, at node 3 we are having q5 and q6, and f5 and f6. Okay, so you need to observe that the ending number of the particular degrees of freedom. After that only I am choosing the next number q4. Here it is q5. Okay, so starting will always the x-axis and ending will always the y-axis. Okay, q5, q6, and external forces as f5 and f6. So right now at node 4 we are having q7 and q8. Okay, so q7 in x direction, q8 in y direction, f7 and f8. Okay, so this is much needed for the next purpose. Okay, that's why you have to do these things, and it is must for all FEM problems. Okay, once you did that, let's go for the element connectivity. Okay, so this is makes the whole problem easier. Okay, so as usual we are having around 5 to 6 columns. In addition to that, I will suggest go for what we call Young's modulus, E, and cross-sectional area A, as well as the one more parameter is that I picked from the previous one, which is global connectivity. Okay, global connectivity. Okay, so that you will remember global connectivity. So let's go for the each elements and defining the position, nodal length, all those things, direction cosines. Okay, so element 1. So for the element 1, I need to prefer its initial node and final node. Okay, so anyways is okay with that. So let's go for node 1 to node 2. Okay, that will be the easier one. Node 1 to node 2 connectivity. So initial node is 1, final node is 2. And later on the element length. Okay, since it is completely horizontal, I will directly going to take that number, that is 40 mm, as my length. Okay, the length of the element 1. Otherwise I should find out, okay, by using the equations that we adopted in the previous video. Okay, and later on let's come to its direction cosines. Okay, so direction cosines L and M, so that will be done with the help of, so L is equal to, so x final minus x initial divided by length of the element. We know that x final is x2, x initial is x1, so x2 minus x1, x2 minus x1 divided by length of the element. Okay, that is 40, length of the element. So x2, x1 value you need to adopt from this table. So x2 value is 40 and x1 value will be 0. Okay, so that will become 40 divided by 40 and minus 40 minus 0 divided by 40, then it becomes 1. So L is equal to 1. Okay, later on M. So the value of M, by using the same thing, but it is a y coordinate, that is final node is 2, initial node is 1, that then it becomes y2 minus y1. Okay, so y2 minus y1 is what? So y2 is 0, y1 is also 0, therefore it becomes 0. So m becomes 0. Okay, so that is you need to write down here. Later on, the Young's modulus, since it is mentioned that only two, only one value is for Young's modulus, and that is common for all the truss members. So write down that the Young's modulus is 2 into 10 raised to 5, and area, that is 100 mm square. After that, global connectivity. So here you should be careful. Global connectivity starts from node 1 to node 2. That is, it starts from node 1 to node 2, means Q1, Q2, later on Q3, Q4. Okay, so it is Q1, Q2, Q3, and Q4. Okay, so like this depends on what? Initial node and final node. After that, node 2.